Now we are going to move to another example. How to apply the equilibrium method in design analysis. Sorry, the previous example is design problems, but now we are going to consider the analysis problem with a photo frame. As you can see here, this is photo frame A, B, C, A, B, F, G. Okay, so the dimension is here. The dimension of the column and the dimension of the beam. The load condition is here. We have load point C and E. The middle of the beam is D. This frame has a section, the same section here, web section. Okay, so I assume that you already know the information of this section, okay, including G and DP and so on, and A wave, AW means the section of the wave, okay, and section modulus, something you already know of this section, I assume. If you don't know, then just stop this video and check in the book, and then play again and continue. This example, we assume Kx equal to Ky equal to 1. K means the effective length ratio, okay? Okay. And B1 equal to B2 equal to 1. We assume that's the effect of a literal translation and non-literal translation case. B1 equal to B2 equal to 1. Then M equal to M. No change, okay? This problem required to determine lambda, the load factor lambda, and that's why we call analysis problems lambda. This is analysis problem. Okay, so remember 8 steps that I already mentioned, and we apply that procedure to analysis these problems. Okay, here we go. This photo frame, first step is to determine redundant, okay? We use same redundant with the previous problem. H redundant and V shear and the bending moment, and we have the 3 redundant, okay? Then we can plot the moment diagram due to each redundant. This moment diagram is due to the axial component. This moment diagram is due to V component, shear, okay? And the last one, this moment diagram is due to M, redundant. Okay, so you remember this one. And what else? M by apply load and redundant. How about the moment under apply load? How about the moment under apply load? Please stop this video and plot the moment diagram due to apply load. Okay, due to apply load. Please plot by yourself. I think it's not very difficult. Then you can plot it very easy. Okay, for example, here like this and like this, and here maybe like this. Okay, and then also this and something like this. Okay, very simple. You can plot it. Then we have a moment diagram due to applied load and due to the redundant. Okay, plot it by yourself one by one, and also the value. Also the value. Input value here, here, and here. And if you have this diagram, then you can follow the next step easily. If you don't have diagram, then some confused. So I recommend you to stop this video and plot diagram first and back to this step. Okay. Now we have M. We can determine M by apply load and redundant at every section point. Every section point. Okay. So we have the point A and B and C and D, E, F, G. We have 1, 2, 3, 4, 6, 7, 8 points at different points. Moment due to apply load at A. Moment due to the redundant M at A. Okay. And moment due to V redundant at A. And moment due to H redundant component at A. So for example, if we determine M at A, then we have M at A equal to this one plus this one plus this one plus this one. Okay, very simple, right? MA equal to minus 525 lambda due to apply load and plus M due to M and plus 15V due to V and 28 due to 8. And we have equation. Okay, and so on. Then we can determine M at B, M at C, M at D, M at E, M at F, and M at G. Every M here. Okay, you can calculate, you can sum up it. Very simple. This is based on the how we can determine this one and how can determine this one due to the previous step. Okay, due to the previous step, you have to plot the moment diagram of due to each component, and then you can write out here. Okay. Now we assume the mechanism. Assume mechanism. Now I assume mechanism at A, plastic hinge at A, at C, at F, and G. Then due to this assumption mechanism, we have moment at A is minus P, moment at C is plus MP, moment at F is minus MP, and moment at G is minus plus MP. What is moment at A? Okay, using again this one, we have moment at A equal to, sorry, moment at A here equal to this one, and it should be equal to minus MP. And similarly, moment at C, okay, moment at C equal to this one and MP. And moment at F this point, F equal to minus MP and equal to this one, okay. And moment at G here equal to plus MP. So again, we have 4 equations with 4 nodes, 1 and 2 and 3 and 4 nodes with 4 equations. Then you can solve this equation, and we have H equal to MP over 10 lambda equal to 7 divided by 900 MP, and V equal to this one, and M equal to this one. Okay, so remember this. It is load factor depending on MP. Okay, depending on MP. If we have MP, we have lambda. Next step is moment check. We have only 4 points already checked MP equal to MP, and we have total of 8 points. Then we need to check 4 other points. Okay, if the M at a point is greater than MP, then the lower bound solution is lambda L. Lambda L means the lower bound solution equal to the lambda that is a solution of a pure step, and multiply by this ratio, MP divided by M at that point. Okay. Okay, then check MB equal to this one and smaller than MP. Okay, good. M at D equal to this one and smaller than MP, then good. Okay, satisfied. ME equal to this one, ratio and smaller than MP, then good. And the last one, okay, it's good. And you can check all of the point is satisfied. Okay, all of the point is satisfied. You can check. Then our solution is correct solution. Then lambda, please remember lambda equal to lambda equal to 7 divided by 900 MP. Okay. Please remember that MP should be considered with the factor shear force, action force, and shear force maybe. Now, if the action force, the effect of shear force is neglected, we don't consider the action load, then what happens? Lambda equal to this one and equal to, because MP of the given section is 247. Okay, then finally we have lambda equal to 1.92. It is the solution of the load factor. Okay, the load factor in case of neglecting the effect of action force. Okay, action load. Because the section is no, then the MP is no. Okay, MP equal to sigma y multiplied by z, and the section has z, and you can check. Now, the action force is considered. In this case, the action force is considered. Okay, now we can consider this member FG. Okay, consider this member FG, because we know that this member is under biggest action force. Okay, compressive action force. PFG equal to this. Please check using the pure step. Okay, then finally we have P, the action force in the member FG equal to 60.3 gives. What else? PY. PY equal to A, the section, And A equal to 13.2 or 0.3 multiplied by sigma y or Fy of the material, let's say steel, or Py equal to this one, okay, Py of the section. And calculate lambda c of x equal to this equation. And we assume this is no brace, then the length is 20 feet, and k equal to 1. Then 12 is transfer ratio between feet to inch, and divide by pi multiplied by Rx, and Rx in this case of the section is 6.65, and multiplied by this one equal to this one, and lambda cy. So let's say, for example, this, then we have x and y, okay, x, and it is y something. Maybe here's x and here's y. Equal to this one, and check, because this one is greater than 1.5, then we may use this one. Okay, equation Pn. I've just explained this equation. However, for plastic design, lambda should be smaller than 1.5. Okay, so what should we do? This is elastic case, but for plastic analysis, we need lambda smaller than 1.5 for plastic analysis, for plastic design. Then we have to use the lateral brace. In this case, we can use we can divide this column into 4 parts using the 4 brace. Okay, so 1, 2, 3, 4. Then we can divide this one. Divide 4. Then now is smaller than 1.5. And now it is plastic behavior. Okay, plastic behavior. Then with plastic behavior, we use this equation to calculate Pn. Now Pn equal to this. Okay. And we have P here, we have Pn here, and it is compression here. Then we have this ratio equal to this one, smaller than 0.2. Then we use this equation, this condition, to check. Then we have P, pi c, and Pn, and this one equal to this one divided by 2, okay, and Mx, and this is 0.8, and Mnx should be equal to 1. And here, Mnx is equal to Mpx, Mp, and equal to this one. It is keep inch, okay, keep inch. The previous one is keep feet, and this is keep inch. Mp, okay, Mp. Mp of the section. This one is Mp of the section. X. Then now we have, because this analysis problem, so we have to determine this one. Now we have this equation, and this one is here. And this one from here divided by 2. Then the unknown is MPC. MPC means the required moment with the consideration of action force. Okay, the effect of action force, MPC, equal to this. And replace MP2 here, and we have MPC. MPC equal to 0.828 MP. Okay, and now lambda. Lambda equal to the original lambda multiplied by this ratio. This ratio. Okay, multiplied by MP. Okay, multiplied by MP here. No, not MP, because we already mentioned MP in this and this one. Okay, we already mentioned MP in this in the first step, right? Then this one is here. Finally, lambda, the load factor equal to 1.59. Okay, so if we consider the action force, then the load factor equal to 1.92. If the action force is considered, the effect of the action force is considered in the column, then the load effect, the load ratio is 1.59, smaller than the original one. Okay, smaller than. So what is conclusion? The action force has significant effect, okay, on reducing the load factor. The load factor, okay, load factor. It is important. So it means in the practical analysis or design, you have to consider also the effect of action force in the member, because we found that that effect is significant and should be considered in the analysis and design. Okay. About shear force. If shear force is considered, so check the effect of shear force. We have Vp equal to this equation, okay, Vp. Vp means shear, the capacity of the section can be determined by using this equation. It's equal to this one. Equal to this one. This equation is already mentioned in some previous class, right? And if you don't remember, please check. And it's equal to this. And we check V of this section, because we know that V of this section is biggest value. Then VEF equal to this, okay, and equal to this one. And we found that the apply shear force smaller than Vp, then it is okay. It is okay. Then MP may be used. Okay, so let me give you one homework. The homework of this week is the problem number 4.19 in the textbook.